Imagine beating a massive 80 billion parameter AI using just a fraction of the compute, simply by teaching two frozen AI brains to talk. Welcome to our podcast, Artificial Intelligence. Papers and Concepts, curated by Dr. Satya Malik and narrated using AI-generated voices.
I am so excited for this deep dive today.
Same here. Our mission today is to rigorously explore the BLIP-2 research paper. We really want to understand exactly how this framework revolutionized vision and language pre-training.
Yeah, and it essentially found a highly elegant way to bridge the gap between images and text.
Right, allowing an AI to process both without completely breaking the bank on compute costs.
Exactly. But to fully appreciate what the researchers at Salesforce accomplished with BLIP-2, we really need to set the historical stage first.
Which in this case is early 2023.
Right. Now, while that sounds incredibly recent to anyone outside the tech world, in AI time, early 2023 is basically ancient history.
Oh, completely. The methodology was just so different back then. It really feels like a decade ago in terms of research cycles.
It really does. At that time, the entire industry was just obsessed with building these massive end-to-end multimodal models from absolute scratch.
Like if you wanted an AI to understand a picture of a dog and write a poem about it, you had to train both parts at the same time.
Yes. The prevailing wisdom dictated that you had to train the vision architecture and the language architecture simultaneously.
Which means updating billions and billions of parameters all at once, right?
Yeah.
Across just unimaginable amounts of data.
It was sheer brute force. Every single time you wanted the model to improve its understanding of how an image maps to text, the system had to update everything.
The visual feature extractors, the language generator.
The cross-modal connectors, all of it. It required massive server farms running constantly.
And that's where BLIP-2 introduces this massive paradigm shift. It asks this brilliant question of, well, what if we just recycle the incredible standalone models we already have sitting on the shelf?
Right. Instead of building from scratch, they grabbed pre-trained vision models, like a vision transformer, and pre-trained large language models, like OPT or FLAN-T5.
And here's the core premise. They kept those models completely frozen. No updating their core parameters. But before we get into the mechanics of that, this podcast is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai.
So getting back to that core premise, holding those parameters completely frozen sounds great for saving computational power.
Oh, absolutely.
Yeah.
But it immediately raises a massive red flag for me.
Right, because if you freeze the language model, aren't you permanently locking it out of learning any new visual concept?
Exactly. If the LLM has never read text describing a specific obscure object, no amount of translation from the vision side will magically make it understand that object, right?
That is a very astute objection, and it highlights a legitimate boundary of this approach. The LLM is entirely dependent on its existing textual knowledge base.
So how did they get around that?
Well, the gamble the researchers took, was that modern LLMs already possess vast near-encyclopedic knowledge of the world. The challenge isn't teaching the LLM what a dog or a sunset is.
Because it already knows the textual representation of those things perfectly.
Exactly. The challenge is simply alerting the LLM that a dog or a sunset is currently present in the image data.
I see. So to visualize the setup, it is like trying to get a master painter, or frozen vision model, and a master novelist, or a frozen language model, to collaborate on a project.
I like that analogy. The old end-to-end way is forcing them both back to school for a decade to learn an entirely new shared language.
Right. Well, the BLI-2 approach is just hiring a highly efficient translator to sit at the table between them.
Exactly. The master painter keeps painting, the novelist keeps writing, and the translator just shuttles the meaning back and forth.
And in this architecture, that translator is called the querying transformer, or the Q-former.
Yeah.
Compared to the models it connects, it is remarkably lightweight, coming in at only 188 million parameters.
Which is tiny in the AI world.
Right. But looking at the mechanics of how it translates, I stumbled over the concept of the information bottleneck.
Ah, yes, the 32 queries.
Exactly. The Q-former uses exactly 32 learnable queries. But an image contains thousands of pixels, incredibly complex lighting variations, and background noise.
It's a lot of data.
So how do 32 tiny queries capture all of that? It feels like trying to suck an entire swimming pool through a cocktail straw.
I love that cocktail straw analogy, actually, because it perfectly illustrates the physical limitation of the architecture.
But how does it actually work in practice?
Well, To understand why it works, we have to transition from the painter metaphor into the actual tensor math.
Okay, lay it on me.
Those 32 queries are essentially a set of learned vectors, and they function through a cross-attention mechanism.
Meaning they are, like, actively searching the image data to pull what they need.
Yes. So the frozen vision model, the VIT, chops the image up into a grid of tiny patches.
Right. And it converts them into high-dimensional mathematical embeddings. Then the Q-former takes its 32 queries and projects them into that same mathematical space.
Scanning those image patches for specific features.
Exactly.
So it's not trying to ingest the whole swimming pool. It's using 32 highly specific filters to pull out just the water molecules it cares about.
That's a great way to put it.
But even then, 32 seems incredibly small. I mean, why not 500 queries? Why not 1,000?
You would think more is better.
Oh, yeah. If the LLM is the brain, wouldn't we want to give it the highest resolution translation possible?
You would think so, but a wider pipeline actually ruins the performance.
Wait, really? Why?
Because if you pass every single visual detail, like every leaf on a tree, the exact shadow cast by a trash can in the background over to the language model, the LLM just gets completely overwhelmed.
Oh, because language is inherently compressed.
Exactly. When human beings look at a photo of a dog catching a frisbee, we don't describe the hexadecimal color code of the grass, We filter out the noise. We abstract it into semantics like dog, frisbee, park.
Right. So by forcing the image data through just 32 queries, the Q-former is forced to extract only the visual features that are actually relevant to language.
Stripping away the useless background noise.
Yes, and compressing the image into its most semantic, language-friendly essence.
The bottleneck forces compression. It curates the visual information so that text brain isn't drowned in pixel-level trivia.
It's like an executive assistant handing the CEO a one-page summary instead of a 1,000-page raw data log.
I love that. But if the Q-former starts as a blank slate, how do you prevent the LLM from just interpreting the translator's output as pure gibberish?
That's the million-dollar question.
Right. There has to be a rigorous onboarding process for those 32 queries to learn what to look for and how to summarize it.
There is. And it is split into a very clever two-stage pre-training process. The first stage focuses entirely on representation learning.
Okay, so what does that look like?
Well, we completely ignore the LLM for a moment and just hook the Q-former up to the frozen vision model.
Just the vision side.
Right. The goal is to force those 32 queries to align their output with human text.
The methodology shows they hit the Q-former with 3 different learning objectives simultaneously during this first stage, which honestly seems like overkill to me.
It does sound like a lot.
Yeah. I mean, why isn't a simple matching game enough? Why do they need 3 distinct mathematical tasks?
Because language and vision connect in multiple complex ways, and the queries need to be robust. The first objective is image-text contrastive learning.
Which is like a massive high-dimensional game of memory matching, right?
Exactly. The model mathematically plots the vector representation of the image and the vector representation of the corresponding text.
And then calculates the distance between them.
Right, and updates the Q-former to pull those coordinates closer together in a shared space.
While actively pushing away mismatched pairs. So the mathematical coordinate for a picture of a cat gets pulled toward the text vector for cat, and actively pushed away from the text vector for car.
You've got it. That builds the baseline alignment. But the second objective is image-grounded text generation.
Okay, how does that one work?
Here, the Q-former actually has to generate text based on the visual features it extracted. It is no longer just matching coordinates.
It has to prove that the features it pulled out contain enough structural information to actually reconstruct a descriptive sentence.
Exactly. So the contrastive learning ensures the query finds the right general concept, and the text generation ensures the query captures the nuanced details required to write about it.
That makes perfect sense. So what does the third objective do?
The third is image-text matching. It is a binary classification task.
Meaning a simple yes or no.
Right. We give the Q-former an image and a text pair, and it just has to output a yes or no on whether they match.
Which still sounds highly redundant, given the first contrastive step. I mean, didn't it just do that?
It sounds redundant, yeah, but the mechanism is different. Contrastive learning looks at the broad macroscopic similarity between the image and text vectors. Image-text matching forces the Q-former's attention mechanisms to look at the fine-grained microscopic relationships. The AI must verify if the relational details hold true.
Give me an example of that.
Well, the text might say the dog is under the table. If the image shows the dog on top of the table, the model must output a negative match.
Oh, I see. It prevents the AI from lazily relying on just spotting a dog in a table.
Exactly.
So by running that rigorous CrossFit routine, contrastive matching, text generation, and binary classification, the Q-former transforms from a blank slate into a world-class visual feature extractor.
Perfectly tuned to the nuances of human language, and that prepares us for stage 2, which is generative learning.
This is where we bring the heavy hitter into the room.
Yes, we finally connected the output of our freshly trained Q-former to the frozen LLM.
The master novelist finally sits down at the table.
Exactly. We take the 32 queries, which now contain a highly condensed, language-aligned summary of the image, and we feed them directly into the LLM as what the researchers call soft visual prompts.
Wait, I want to make sure I understand the mechanics of a soft prompt.
Sure.
Because the LLM has never seen an image in its life. Its entire architecture is designed to ingest text tokens, which are just strings of numbers representing words.
Right.
Are we essentially disguising the visual data as a string of text tokens?
That is essentially it, yeah. The Q-former projects its visual queries into the exact same mathematical dimensions as the LLM's text embeddings.
Oh, wow.
And we prepend these visual embeddings to whatever text prompt the user inputs. We are basically tricking the language model into processing visual information as if it were a highly complex, pre-written paragraph of text.
That's incredibly clever. And because the LLM remains completely frozen throughout this entire operation, it avoids a major issue in machine learning called catastrophic forgetting.
Yes, catastrophic forgetting is a massive hurdle in AI development.
Right, because if you unfreeze an LLM and force it to learn visual weights, it will aggressively overwrite its previous text-based knowledge.
It basically forgets how to write well, just to learn how to see.
Exactly. But by freezing it, it retains its pristine ability to write, reason, and follow instructions. It just suddenly gains eyes.
And the outcome of combining that pristine reasoning with the Q-former's vision is what shocked the research community. The performance numbers are just staggering.
The David versus Goliath statistics in the paper are phenomenal. They benchmarked BLIP-2 against Flamingo 80B, which was DeepMind's flagship state-of-the-art model at the time.
And Flamingo was a behemoth with 80 billion parameters.
A model that required staggering amounts of compute to train end-to-end.
Absolutely massive.
And when they ran the zero-shot VQAV2 test, which for you listening is a visual question answering benchmark, where the model has not been specifically fine-tuned on the test data format.
Right, a very tough test.
BLIP-2 outperformed the 80 billion parameter Flamingo by 8.7%.
Which is huge. An 8.7% jump on a zero-shot benchmark in this field represents a massive generational leap.
But the absolute mic drop is that BLIP-2 achieved this dominance using 54 times fewer trainable parameters. 54 times.
It's hard to even wrap your head around that.
Because the massive vision model and the massive language model were kept in the freezer, the system only had to update the tiny 188 million parameter Q-former during the pre-training process.
And the implications for the broader tech ecosystem were profound. It proved that achieving state-of-the-art multimodal AI did not require boiling the ocean.
You didn't need a dedicated supercomputer cluster to teach a language model to see.
Exactly. You just needed a highly efficient bottleneck to act as a bridge.
And the practical applications go far beyond benchmark scores, because the researchers specifically utilized instruction-tuned LLMs like Flan T5 models already optimized to follow complex human commands. BLIP-2 instantly inherited those capabilities.
Yeah, the paper highlights some brilliant emergent behaviors where the AI isn't just labeling objects, but actively reasoning about them.
The qualitative examples really demonstrate the semantic depth of the Q-former's translation. Like, one example shows a beautiful photograph of a sunset over the ocean. And the human prompt does not ask, what is in this image? The prompt asks the AI to write a romantic message that goes along this photo.
A very abstract request.
Exactly. And the model outputs. Love is like a sunset, it's hard to see coming, but when it does, it's so beautiful.
I mean, to generate that, the system must perform multiple abstract steps. The Q-former identifies the visual concept of the sunset.
Then the LLM processes the human command.
Right, understands the abstract concept of romance, maps romance to the visual concept of a sunset, and generates a poetic analogy.
There was another example that demonstrates visual knowledge reasoning. The user uploads a photo of the Merlion statue.
The one in Singapore.
Right. The user asks, which city is this? The AI correctly states Singapore. Then the user pushes further and asks, why do you think so?
And the AI responds, the city has a statue of a Merlion.
It successfully identifies a specific geographic landmark from raw pixels, queries the frozen LLM's vast knowledge base to deduce the location, and then articulates the logical steps of its deduction.
It's amazing. And it also handles visual common sense reasoning.
Oh, the chicken picture.
Yes. There is a picture of a man cowering as a chicken flies at his head, and the AI accurately explains why the man looks terrified.
It understands the physical dynamic between the objects in the frame.
It's incredibly impressive.
It is, but, we have to maintain our skepticism and look at the entire picture. The researchers were very transparent about the flaws in this architecture.
They were, yeah.
And exploring where it breaks down is just as informative as exploring where it succeeds.
Well, the limitations fundamentally stem from the very architecture that makes it so efficient. The reliance on frozen models is a double-edged sword.
Right, because by freezing the LLM, you freeze its capabilities, but you also permanently lock in all of its bad habits and factual errors.
The confident hallucination problem.
Yeah.
If the LLM has inaccurate knowledge baked into its weights, the Q-former cannot correct it.
It just passes the mic to a flawed speaker.
Exactly. The paper illustrates this with a specific test. The researchers provided an image of Albert Einstein and asked the model to write a famous quote by him.
And the model confidently generated the quote, "The world is a book, and those who do not travel read only one page."
Which, outside of motivational internet posters, is generally attributed to St. Augustine, not Albert Einstein.
Right, so the visual pipeline performed flawlessly. The Q-former looked at the pixels and accurately translated them into the concept of Albert Einstein.
But once that concept was handed over to the frozen LLM, the LLM's flawed internal knowledge retrieval took over.
It pulled an incorrect quote and presented it as absolute fact.
Yeah. And there is an even more revealing failure in the paper regarding common sense reasoning.
Canada trip.
Yes. A user provides an image of a man wearing a casual button-down shirt and dark shorts. The prompt asks, can I wear this for my trip to Canada in December?
And the model's response is fascinating. It says, yes, it's a nice shirt and shorts, but it's a little too casual for a trip to Canada.
It completely misses the point.
Completely. The model thinks the primary issue is a lack of formality, completely ignoring the fact that wearing shorts in a Canadian December will result in severe frostbite.
It fails to connect the visual input shorts with the external world knowledge of winter weather patterns.
And this failure perfectly illustrates the boundary between the Q-former's translation layer and the LLM's reasoning layer, doesn't it?
It really does. The Q-former successfully executed its job. It translated the image into man in shorts.
But the LLM then went down an entirely illogical reasoning path regarding fashion etiquette instead of climate survival.
And you cannot fix that reasoning failure by tweaking the vision system. The flaw lies purely in the frozen brain.
Wow. There is one final limitation discussed in the sources that I want to drill into because it touches on the data itself. The model struggles significantly with in-context learning.
Right. And for you listening who might be unfamiliar with the term, in-context learning is the ability to grasp a new pattern on the fly from a few examples provided in the prompt.
For instance, showing the AI, image A is a cat, image B is a dog. Now look at image C, what is it?
Exactly. And BLIP-2 fumbles that kind of sequence.
But why? I mean, if the LLM is so powerful, why can't it recognize the pattern?
It comes down to the shape of the pre-training data. BLIP-2 was trained almost exclusively on datasets containing single, isolated image text pairs.
Like one picture of a dog, one caption saying dog.
Yes. The model learned to process the world in discrete, disconnected flashcards.
Ah, so it never learned how to look at a flowing sequence of events.
Exactly. Contrast that with the Flamingo model we discussed earlier. Flamingo was trained on interleaved datasets.
Because web pages are messy.
Very messy. You have an image, a paragraph, an ad, another image, another paragraph. Flamingo trained on that messy sequential data.
So because Flamingo absorbed that interleaved structure during training, it naturally understands how to look back at previous examples in a prompt to decipher what the user wants.
Precisely. BLI-2 lacked that specific dietary input, so it lacks that specific output capability.
So, synthesizing all of this, what is the ultimate takeaway for you, the listener? Why does a paper from early 2023 matter to the trajectory of AI today?
It matters because it laid the foundation for the modular AI revolution. Sticking massive frozen models together using highly intelligent bottlenecks like the Q-former drastically lowered the barrier to entry for AI development.
It democratized research.
It did, but observing its limitations, the inherited hallucinations, the rigid reasoning, the lack of in-context learning, reminds us that efficiency has a ceiling.
The bottleneck glue is only part of the equation.
Right. We still need dynamic, interleaved training data to push these systems toward true, fluid reasoning.
You can build the world's greatest translator, but if you only ever teach it to translate single, isolated sentences, it will freeze up when you try to have a natural conversation.
That is an excellent summary of the paper's core tension.
I want to leave you with a final thought to mull over. We spent this deep dive exploring the bridge between vision and language. We took a frozen visual brain and a frozen language brain and proved that a tiny 32-query bottleneck is all it takes to perfectly synthesize them.
Right.
The logical next question is, what other frozen domains are waiting to be unlocked?
The possibilities for modular expansion are practically endless.
What if we take a massive, frozen audio model that detects the microscopic acoustic signatures of failing machinery and connect it to a frozen LLM using an audio-specific Q-former?
Or a frozen robotics model that understands proprioception and spatial mechanics.
Or even a frozen model trained entirely on human genomic sequences? If the bottleneck approach is this robust, we might be just a few tiny translators away from an AI system that can natively cross-reference and reason across every single scientific discipline and sensory input known to humanity, all just by teaching the frozen brains how to talk.
Thank you for listening. If you enjoyed this episode, please subscribe and join us next time.